pretty impressive in itself because technologies come and go, and some technologies don't even arrive. We hear all about them and we get excited, but they don't happen. So Bluetooth has really survived, but it's not just surviving, it's thriving. So to put that in context before we start with the topic, in the year 2000, there were 800,000 Bluetooth devices that shipped in that entire year. So that was near the beginning of Bluetooth's history. But now we have 10 million Bluetooth devices shipping every single day. So it's really ubiquitous. It's definitely one of the technologies to know about, especially as the age of the Internet of Things is upon us. Who here has actually done some development with Bluetooth on any platform? Good few of you, excellent, that's great. So you may already know then there are 3 flavors of Bluetooth these days, or 3 Bluetooth technologies. We have 2 radio communications technologies. One is called BR-EDR, that's basic rate, enhanced data rate. That's the original Bluetooth. It's for forming point-to-point connections between devices. It's a cable replacement technology. Throw the cable away. That's what that gives you. If you have wireless headphones for music, that's almost certainly that flavor of Bluetooth. We also have Bluetooth Low Energy, and it can form these point-to-point connections, but it can also let you broadcast, which means one transmitting device can communicate with many other receiving devices. If you saw me talk last year, I talked about beacons. Beacons are a great example of Bluetooth Low Energy in its broadcast mode. Last year, though, we released something completely new, and that's Bluetooth Mesh networking, and that's what I'm here to talk about today. And Bluetooth Mesh lets you form networks of potentially many thousands of devices, all communicating with each other. This is an entirely new form of Bluetooth, and in fact, it's not a radio technology. It's a networking stack. What we had in mind for Bluetooth Mesh, and I'm sure it will be used for all sorts of things we didn't think of, because that's typically what happens, in the first instance was smart buildings and smart lighting systems. I'm talking about commercial buildings more than the smart home. Smart home, perhaps, but most certainly large commercial buildings. If you look around this building, have a look at all the lights that there are here, for example, great example. Possibly sensor networks, we see some use there. Possibly things like asset tracking and networked indoor navigation systems as well. So lots of things, use cases that Bluetooth Mesh will be applied for. The primary thing we were designing for, though, is lighting and commercial buildings, truly smart buildings. Want to make sure you understand the relationship between those 3 technologies before we drill down and focus on Bluetooth Mesh. So at the bottom of the slide here, we have the radio technologies, radio communications. That's what Bluetooth is. And those 2 flavors of radio are down at the bottom there. BR-EDR for steady streaming of data, things like audio, music, for example. Bluetooth Low Energy, very optimized for power efficiency. Often you can run devices off small batteries for literally years. That's what it was designed for. If you've got an activity tracker like a Fitbit, it's using Bluetooth Low Energy. If you've got a smartphone, yes, that's a joke, it's using both. It supports both flavors of Bluetooth. That's typically the case. But Bluetooth Mesh networking is a networking stack, and it sits on top of, makes use of the Bluetooth Low Energy radio. You, of course, already have APIs for Android that let you work with Bluetooth Low Energy, and I guess from the hands you showed me earlier, some of you have already worked with them. They've been there in some form at least since Android 4.4 in reality. So they're pretty mature and actually very well designed. So let me talk about Bluetooth Mesh. I want to just give you an understanding of the fundamental concepts, some of the terminology, and so on, and then I'm going to talk to you about how it's relevant to you as Android developers. Let's start here. So one of the things that's fundamental to, I think, all wireless mesh technologies, because there are several, we have competition, is that devices can communicate with other devices that are out of radio range. So that's different. The way that works is through what we call multihop messaging. A device like a light switch might send a message saying, please switch on, but that message will get relayed. It will bounce across the network from device to device until it reaches its final ultimate destination, which may be a very long way away. Bluetooth Low Energy also already has a very healthy point-to-point range. Outdoors, it's hundreds of meters, 300, 400 meters for sure. I've tested that myself because I don't believe anything anyone ever tells me. So I did my own testing. It's like, oh, wow, it really is hundreds of meters. That's impressive. But with Bluetooth Mesh, we can relay up to 127 times. It's a 7-bit field that controls that. So you can imagine you can envelop very large buildings, in fact, collections of buildings, with a Bluetooth Mesh network. A university campus, a business campus can have an entire Bluetooth Mesh network. Multipath is different. Other networking technologies, mesh networking technologies, don't do this as far as I know. There are probably two priority one requirements that Bluetooth Mesh was designed for. Lots of detail, but two real headline design goals, if you like. I was actually in the room for the first 2-day workshop where requirements were discussed in Cambridge, England, about 3 years ago. One of those was reliability. Security was the other one, but reliability really important. Some really tough engineering problems to solve to make reliable mesh wireless communication work in a building full of metal and people and all sorts of problems. It's quite hard. To make it harder, things like lights are almost all about multicast operations. You rarely are just switching one light on. Normally you're controlling large collections of devices wirelessly all in one go, and they must work, and latency must be very low, and they may be out of range. So all sorts of quite hard problems. So rather than choose easy goals like a thermostat, a wireless thermostat is a very simple device, very easy, the bar was set very high right from the start. Let's make a really reliable technology that works well with the typical requirements of a truly smart building. And multipath is one of several strategies that are employed by the technology to achieve high levels of reliability. And basically what it means is that any message sent by a device, it's all message oriented, will travel by multiple paths through the network. Pretty much by magic. There are no routers or routing rules or tables that you have to configure and maintain. It's inherent in how it works. So if a message takes a certain path and finds that it blocks because a device is broken, it can't use it to relay itself, doesn't matter, because another copy of that message should make it through one of the other paths. This is just architectural redundancy. Okay, it's a common concept in architectures that architects, of course, exploit all the time. So what is the network? Well, first of all, if you consider devices that are not part of your network, you just bought something from the shop, you take it out of the box, it's Bluetooth Mesh compatible, but at that point in time, it's not part of your network because networks are secure and essentially closed. You can't have ad hoc devices turning up and using your network. They have to be brought into the network as fully fledged members. I liken it to an exclusive club. You have to be a member. There's a process you therefore go through with any new device, which is called provisioning. It involves typically a smartphone or a tablet running a standard Android application, and its job is to equip the new device with a series of security keys, and it's possession of those keys that makes it a member of your network, because your network has unique keys that are unique to it and only it, different to your neighbor's network, for example. At the same time, you'll probably also do some configuration. So you take the device out of the box, press a button on the application, give it its keys, and probably give it some other information about other devices it might want to work with. Now, I've already mentioned messages. All communication in the mesh network between devices is message-oriented, so lots of very common and understandable concepts because it's message-oriented. In terms of classes of message, we can get and set values on another device, and we can be informed of current values through things called status messages. There's an exciting animation for you. Not surprisingly, because we're sending messages, there has to be an addressing scheme. Have to be able to address the devices we are sending our messages to. And in fact, there are 3 types. Unicast addresses are a unique ID for every device. Surprisingly, you hardly ever use them. You use the unicast address when you're configuring a new device. Pretty much that's the only time. The rest of the time, you're going to use group addresses or virtual addresses, which are 2 different ways of addressing a collection, a set. of devices. Group addresses are the most common. They usually correspond to physical parts of a building, like a room, that kind of thing. And the reason we always use group addresses, even if there's only one member of the group, which I shall explain. So group addresses look like that. So the user's going to give them a human-readable name. They're identified by a 16-bit value internally, but they allow us to reference collections of devices, usually of a given type in a given place. Now, the reason we like group addresses is this. The messaging system's based around the publish and subscribe approach. You're probably familiar with that kind of pattern in messaging. So in my example here, when I configure my light switches, I will configure them to publish to, in other words, address when transmitting, a group called hallway lights or something like that. And when I install the lights in my hallway, I'll configure each of them to subscribe to messages that were addressed to hallway lights. Now, the key to the magic here is that the lights actually don't know anything about, the light switches don't know anything about the lights they're controlling, and the lights themselves don't know anything about the switches that are controlling them. Okay? They're completely decoupled. The switches just broadcast to that address, job done. The lights just listen for messages to that address and respond to them, but the two are decoupled. And the benefit is that I can make changes without having to reconfigure everything. I can install new lights in my hallway, I can replace broken ones, I can add new switches, and I have to do very little configuration change at all. Just the new device is affected. Hotels, by the way, often have 50,000 lights, so you really want to keep maintenance and configuration tasks at a minimum. So we also have this thing called scenes. Almost at the end of the theory here, a couple more slides on theory. Scenes are about automation. So a very common requirement is that you want to kind of orchestrate a collection of changes across lots of different types of device all in one go. It might be because the temperature has changed. It might be because someone's walked into a room and an occupancy sensor has detected your presence. The lights come on, the blinds come down, the heating comes up a little bit. All that happens all in one go. And this feature called the scene allows you to define sets of configurations to apply to lots of different devices in a single action. Last bit of theory. This is a really important one. This is the model. If you've worked with Bluetooth Low Energy, you'll know about services and characteristics and descriptors. We rarely talk about such things in the world of Bluetooth Mesh, but we do talk about models. So models are effectively standard software components. They're all defined in the specification, very granular, and a product's capabilities and behaviors are a consequence of the collection of models it implements in its firmware. So if you're a product designer, effectively you're picking standard models from the spec to equip your device with, and that's what gives it its wireless capabilities, which allow it to participate in the mesh a certain way. So we've got a number of lists of these models defined. The whole point here, by the way, if you're not clear on this, is that it means you get interoperability across vendors. Okay, so you could buy your lights from one vendor, your switches from another. They will work together. You may be thinking, yeah, and that doesn't sound very exciting, but I can promise you I've been speaking at building and smart home events for years, and in that world, this is a big deal. They're not accustomed to that. There's lots of vendor lock-in, old-fashioned business models, so they really want this. So we have lists. One of the lists is called the generics, the generic models. They're called generics because they are applicable to any type of product. Simplest two are on the screen there, the generic on-off client and the generic on-off server. They're for switching things on and off. How many types of device can we switch on and off? Answer, lots. Okay, so that's why it's in the generics list. Clients and servers. Servers contain state, basically data items that represent the state the device is in. And often if you change a state value, the device will respond in some way. So that's how you can exercise control over devices, by sending a message that will set the value of a given state data item inside a model. Okay? Clients don't contain state, they just produce and consume messages. So let's bring the theory together and let me show you what this would look like in a real kind of scenario with different types of products, and then we'll talk about Android specifically. As always, by the way, you like this. Guess who didn't press start on his stopwatch and has no idea how he's doing for time? That's right. They'll kick me off stage, or you'll just walk away, and then I'll stop. So the graphics already tell you, I'm sure, I've got a light switch, I've got a light, some lights, in fact, and I've got a sensor of some sort here. Let's explore the models that they would typically have inside them so that we understand the granularity and how the interoperability between devices works. So first of all, I probably want to be able to switch my lights on or off. So you've already encountered this. I'll have the generic on-off client model on the switch, the generic on-off server model on the lights, which contains a state called generic on-off. It takes a 1 or a 0 to indicate whether it's on or off, okay? It's not rocket science. Beyond the world of generics, we have some very specialized models specifically for lighting. Lighting, it turns out, is really complicated. You have no idea. Of those 2 days I sat in a room talking through requirements, at least a day was spent talking about lighting. I was shocked, afraid, lots of things. I had no idea there was so much to it. So the lightness server allows you to dim and brighten a light. Sounds very simple. We also have the generic lightness model, which also seems to do the same thing. But it turns out that human perception of brightness is not linear. So you need a special linear algorithm for the changing in brightness to look right for humans. So that's why we have this special model for controlling brightness. HSL is hue, saturation, and lightness, so that's for colored lights. So we can change the color of lights with that model inside them. LC stands for lighting control. This is a special model designed to work with sensors. And with one more concept, I'll show you how all this stuff works together. That other concept is called the state binding. So models contain states, data items. You can configure relationships between them so that if one state value changes, it automatically triggers a certain type of change in another state value in another model. So we can build relationships between them. It's very flexible. Now, imagine my sensor is an ambient light sensor. Its job is to measure the ambient light level in the room. And I probably have an objective to maintain a consistent light level in the room throughout the day. It's a consequence of the artificial light and the light coming in through the window. Those two things together give me a certain ambient light level. Now, I want to do this for two reasons. One is to save money. I don't want the lights on when there's bright sunshine coming in through the room. That's a waste of money. It's not good for the environment either. And in some parts of the world, there are actual laws or regulations I have to comply with around this now. The other thing is I want a nice environment for my employees to work in because I'm a nice employer, if you can imagine that. So the way this works is as follows. The ambient light sensor is sampling the light level at intervals, maybe once a second. And for each of the readings it takes, the sensor server model inside it will publish a message containing the latest reading to a certain group address. The lights have subscribed to that group address, they're receiving those readings. And they're all processed by the light LC server because it's about lighting control. Now, there's a state inside the LC server concerned with lightness, ambient light levels, but it's got a binding to the lightness server. So as the sensor is saying, hey, it's getting brighter, that state binding is causing the lightness server to turn the lights down to keep it steady. Okay? And if it starts to go dark because it's late in the day or it's a big cloud or we're in Britain or something like that, then of course the opposite happens and the lights subtly come up. This is all very subtle, very granular. And we can do lots of things like that. That could be an occupancy sensor, and by walking into the room, there's a binding with the generic on-off server, and the lights come on. Okay? And we probably have something to do with scenes in there, and we probably have stuff to do with time. We can propagate time across the network as well. So that's how models get used in real products. Android. I was supposed to talk about Android. I'm going to do that bit now then. Most of you are still here. That's fantastic. So, recap, or perhaps for some of you, some new information. So Android's had Bluetooth Low Energy APIs since 4.4, effectively, and they're very good. They've been through some evolution, big changes at 5. I like them a lot. The first thing you tend to want to do with any Android application is discover Bluetooth Low Energy devices that are in the environment. excuse me, such devices that want to be discovered are doing something called advertising. They're broadcasting small packets of data saying, hello, I'm here. You have a whole bunch of classes to allow you to kick off the discovery process, which is called scanning. You can set filters and prioritization rules and things like that, but you can use them to find a selection of candidate devices which you might then present to the user for them to select. You already have all this stuff. This has nothing at this stage to do with Bluetooth Mesh. Once you've discovered devices and decided through some mechanisms such as user interaction which one you want to connect to, or which ones, you have other classes. Bluetooth GATT is the kind of the master class which gives you big libraries, almost like a facade API, lots of things you can do. You can initiate all sorts of operations through it. They're all asynchronous. You get callbacks to an implementation of Bluetooth GATT callback. And then data is kind of structured on a Bluetooth device in a hierarchy. We have these three classes, services, characteristics, and descriptors that form that hierarchy that we're going to play with. This is Bluetooth Low Energy, not Bluetooth Mesh at this stage. Bluetooth Mesh, however, was designed to allow in-market devices like smartphones with suitable APIs, which Android has, to be able to securely connect to and interact with a mesh network and the devices in it. So we have a device role that any device can play. Doesn't matter what type of device it is. It could be a light, it could be a thermostat. It's called the Proxy. It's a software capability, and you can switch it on or off through that configuration process. You can say, yeah, this device needs to be a proxy. It's in the reception area. That's where people are going to want to use their smartphones to interact with the building. Oh, there you go, Android apps. So that's what it's for. It allows in-market devices like Android applications to talk to the mesh network. So how does it work? Here's the architecture. Going to get a bit more technical now, I guess. Inside the dotted line, we have a Bluetooth Mesh network. Outside of it, we have a standard Android device like the ones you all have in your pockets. One of the devices or more has been designated a proxy node, and inside it, it has a Bluetooth Low Energy service called the Mesh Proxy Service, a standard service we defined with a well-known published UUID, so you can identify it. It's got two characteristic data items inside it, one called Mesh Proxy Data In, one called Mesh Proxy Data Out. And then from your Android application, you will use your Bluetooth Low Energy APIs to write data to that proxy node's data in characteristic. This is how you inject messages into the network. And you'll receive notifications from the other characteristic, which encapsulate mesh messages. Mesh messages are small, 29 octets, highly compressed to be very energy efficient. That's one of the reasons. So you can afford to wrap these things up in Bluetooth Low Energy packets and use your standard APIs. So let's have a look at what PDUs look like. Now, I might scare you at this point, I might not, I don't know. There's some detail to know here, and we don't have time for it today. You'll have to look at the spec for this part, or a resource I might mention later on. But basically, you will be reading and writing proxy protocol PDUs. That's their name. And they have a structure as shown, three major parts. First is a couple of bits concerned with segmentation and reassembly of long proxy packets. Then there's a type field. There are actually 4 different types of proxy PDU. Normally, you're going to work with network PDUs. Those are effectively those messages I've been talking about, things that can switch things on and off, change levels and stuff like that. And then there's the payload, which has the mesh message itself sitting inside it. If we look more closely at the payload, we'll see it's broken into 3 major parts: network, transport, and access. And these correspond to the names we have for layers in the mesh stack. The network segment, part of your payload contains things like source and destination addresses. There's more stuff to do with segmentation and reassembly, but for mesh messages rather than proxy messages in the transport section. And the access part, that's the top layer of the mesh stack. That's where we put our message opcode to identify the message type and parameters associated with it. So I'm a message that means please switch on, and the value I'm setting you to is 1 for on. That all goes there right at the end. So you have to formulate this packet. It's a byte array. You have to put the right bytes in the right place, the right bits set to the right value, because there are no mesh APIs today, but it's not hard. I did it in JavaScript, by the way, so how hard can it be? There's some security you also have to apply, though. So you cannot have an insecure Bluetooth mesh network. It's not optional. Bluetooth Low Energy, all the security features are optional. You can have a device that's completely open if you as the manufacturer think that's appropriate. You know, the manufacturer has to decide. Not with Bluetooth mesh, because you can't allow one manufacturer to weaken the security of the whole network. So all security is mandatory. And there are lots of aspects to this I don't have time for today, but one of them, excuse me, is that all messages are obfuscated so that kind of pattern analysis techniques to try and track devices through the network can't be applied to addresses. You have to obfuscate the network header. Again, it's very straightforward. You typically work with two distinct security keys, one called the network key, or net key, and one called the application key. The network key is used to encrypt using an authenticating algorithm, so you can't spoof messages because they're authenticated, and you encrypt all the sort of network information that's not obfuscated. Okay, that all happens there. And largely, every device in your network will have the network key and therefore be able to do things like relay your message without necessarily knowing what sort of message it is. Because that's the access layer at the top, and that's encrypted and authenticated with a separate key called the app key. And only devices that are deemed to be part of the same application, so maybe lighting is one application, heating is another application, aircon is another application, they all have distinct keys, so they're separated from each other cryptographically. They can help each other in network operations because they have the network key, but something like a light can't decrypt the information coming from your physical security barriers at the front of the building because it has no business knowing that information. Okay? So you have to do this too. At the end of the day, though, you're probably making a single API call to apply each of the required types of crypto to the three sections of this packet. Some work to be done, but it's not hard. If you do it in JavaScript, you can definitely do it in Java. The question might arise, well, how does my application know its keys? Again, it's through that provisioning process that happens right at the very start of a device's kind of life in the network. But it applies to your smartphone application as well, not just to things like lights. Anything, absolutely anything that wants to communicate in your mesh network has to be provisioned, because if it's not, it doesn't have those keys, so it's not part of the network and it can't formulate packets correctly and securely. So your device is going to have to support provisioning, which involves it acting as a Bluetooth GATT server and exposing a couple of services itself, both concerned with provisioning, both suspiciously similar looking in structure to the proxy stuff. There's an in and an out that you read and write values from. And through following the appropriate procedure and making use of those classes, which you'll have from Android 5.0 onwards, you'll be able to make sure that your application has been provisioned as well. So your user is going to install your app. You're going to say you need to provision. There'll be some guidance in your help, and they'll provision it so it can work with the network, probably using another app from a vendor of one of the devices they've installed. Code. So if you've not seen Bluetooth Low Energy stuff before, this will be unfamiliar. If you have, it'll be very familiar. Very simply, you work with UUIDs when you're working with Bluetooth Low Energy. All services and characteristics are of a uniquely identifiable type. You will essentially construct for yourself an instance of the Bluetooth GATT characteristic object. You'll have a function that creates that byte array I've just described in my two slides, in which I've kind of sneakily not gone into any detail on there, but it's just bytes and bits. It's very straightforward. You'll set a value on the characteristic that you want to inject it via, and then you'll just call write characteristics. That writes to the proxy node, and then it will get propagated across the mesh network. How do you actually develop stuff? There are quite a lot of Bluetooth mesh developer boards out there now. The ones depicted on screen are from Silicon Labs. Cypress Semiconductor have them. Nordic Semiconductor just had a big release of their mesh stack for their device types. You need some kind of device to develop against, though. The one I'm using all the time right now, though, is an open source real-time operating system called Zephyr. If you've never heard of Zephyr, you should definitely Google for it. Zephyr runs on device. You program in C++. The people behind it are the Linux Foundation, so a lot of the developers involved in it are Linux kernel developers. They really know their stuff. It's very lean. I typically use it on a BBC microbit. If you've heard of one of those, they're tiny, they're cheap, they cost 15 euros, small amounts of memory, but you can fit Bluetooth mesh on them. Okay, so that would be the place to start. Get yourself a device and start coding. Hope that's given you a good flavor for what Bluetooth Mesh is about and some pointers as to where to start. I'd love to see the community get behind this because whilst, yes, you can create Bluetooth Mesh applications using the Bluetooth Low Energy APIs you already have, it's not hard, but it's work. You could make it easier with an open source library API for the Proxy protocol that I talked to you guys through.